Okay, now I'm going to introduce my work together with Pierluigi Nuzzo from University of California and Patrizio Pellicione from Gran Sasso Institute. And it's about incremental refinement of goal models with contracts. So first of all, let's talk about requirements in system design. So what is the role of requirements? Because usually missing or erroneously formulated requirements can have a negative impact on the design of the systems. So let's see what is the relationship between requirements that should be something that formulates what the system should do, and the system specification is instead what the system is prescribed to do, describe what the system actually does. And so in order to bridge this gap between the system and the specification, we have to make some assumptions on the environment as a property the environment has to hold. So in order to trust that our system design is correct, we want to be able to formulate somehow, more or less formally, that our system specification under the assumption that we made in the environment satisfies our requirements. Okay, so in this talk we talk more about the requirements, how we model them, and how we formalize them. So traditional, or like one way to model requirements is through the use of goal models, which has been used over the years to effectively capture the designer intention in a sort of hierarchical structure, and is mostly following a wish approach designed to objectives, right? So we have the requirements, and we formulate each requirement in terms of goal, while the environment assumption, we formulate them in terms of expectations that we want, that we assume that are the environment where the system is going to be deployed will observe, or domain properties, which are like physical laws of the environment. And so the refinement process mostly is informal and can follow a, for example, here you see an example of end refinement, where we have an hierarchical structure of goals, where the goals are decomposed in sub-goals, and the refinement process can basically find out possible sub-goals from parent goals, or identify connection between the sub-goals and parent goals. So in this example of goal models, we can see that the assumptions are basically treated as any other behavior that is only finally assigned to be, okay, this is an expectation of the environment, or this is domain properties. And this is not too much modular, because every time we want to change something in some goal, we have to reformulate all the assumption and check the whole tree. So we would like to have something more modular, and something where we would like to express under which condition each goal hold, and we want to do that at each step of the refinement process. Ultimately, the goal, I mean, one of the main problems of goal models is to establish definitely the correctness of the goals. What does it mean, correctness? Well, it means that first of all, the goals has to be consistent. So we have consistency among goals, means that there are no contradictions, and also completeness. So that there are no behaviors left unspecified that could result in a violation of higher level goals. Okay, although the lower level goals are satisfied, you somehow don't satisfy the higher level goals. Okay, so these are the main problems that we want to deal in goal models. So let's talk now about the contracts, what the contracts do. Specifically, assume guarantee contracts. So what is an assumed guarantee contract? So, well, for our purposes, is a triple where we have a set of behaviors which represent the assumptions, so the properties that we want to be satisfied by the environment, where our system components operate, and a set of behaviors that represent the guarantees, so the properties that the system components are allowed or not allowed to perform. And these set of behaviors are expressed over set of variables, right? Over set of system components. So for our purposes, we can also not talk about the variables and only define the contract as a tuple of assumption and guarantees. So what are these system components? What is the relationship with the contract, right? So while on one hand, the components represent the design elements that express the behaviors over the variables that we have in our systems, on the other hand, the contract somehow encapsulates all possible behaviors, so defines a boundary that we can use that component, okay? So in a sense, it's related to the goal, because in a goal, you don't specify exactly the implementation that you want, but you would like to have, okay, what are all the possible implementation I would like to have in my requirements? And the same way, the components do not restrict the environment that we want to use, but the contract do, because we declare explicitly all the environments that are acceptable by our contract and the limit of our operations with the guarantees. So the components we said is more an implementation, so it's an architectural solution, while on the other hand, the contracts are on purpose abstract in order to encompass all possible different implementations. So how do we formally establish the satisfaction of a component with respect to a contract? Well, we can say that a component, which in this case is represented by the letter M, is also which is also a set of behaviors, and behaviors are basically can be anything, but we can think of a behavior as a set of, a sequence of infinite states of a system, so assignment to the system variables. So this component implementation satisfy the contract whether the components and the contract that are defined over the same variables, and all the behaviors of M are included in the guarantees of the contract when considered under the assumptions. Okay, so we can also define this component, which is represent the maximum implementation that we can have. What does it mean, the maximum? It means that it includes all possible behaviors that satisfy the contract, where this symbol denotes the complement of the assumptions. Okay, let's see what operation we can do with the contract, traditional operation from the contract theory. And first of all, we have to saturate all the contracts. So, why? Because we want to express we want to be able, we want the guarantees to express all possible implementation. So we can actually redefine the guarantees of each contract, so that in the guarantees we basically have the maximum implementation of the contract, and this is equivalent to having a non-saturated contract, because the equivalence is checked only on the maximum implementations. And so the operation between contracts, so assuming that we have a contract C1 with the assumption guarantees A1, G1, and a contract C2 with assumption guarantees A2, G2, we can either compose the contract. In this case, the resulting contract, so the composition produces a new contract, which demands, as you can see, the environments to operate in both contracts, because in this case we take the intersection of the assumptions, and or we can choose to perform the conjunction, where we require the resulting contract to operate in environments that satisfied either, but not necessarily both, the assumption of the original goals. And finally, we can compare contracts by basically with this refinement operation, where in this case a C1 refines C2, meaning that the assumption of C1 are relaxed, so are bigger, and the guarantees are smaller in the sense of the set. The set of guarantees is smaller, and so in this case is stronger. Okay, so these are the basic operations you're going to use. Now, going back to our problem of goal modeling and requirements, how do we use contracts? Well, simply we define a contract for each goal, and we concretize. So far in the theory only talks about the set of behaviors, but what actually are these behaviors? Well, we assign a formula for the assumption, a formula for the guarantees that in our context we're going to use psi for the assumption and phi for the guarantees. And for example, in our paper we show this vehicle platooning example. So on one hand we have an informal goal representation that, for example, in this case we want a goal. So in the vehicle platooning we basically have we have to model a leading vehicle which is guiding a several following vehicles, right? So one goal can be, okay, if the leader transmits the correct data, then the following vehicles will follow within a given bound with a certain propagation delay. So we set the bounds of our goal, and we say, okay, the propagation delay has to be a maximum 0.01 second, and so on. And we assume some data that's being correctly transmitted. Instead of using a goal model, we define a new formal model, which we named contract-based goal tree. And in these formal models, we have two kinds of nodes, which can have goal nodes where each goal is formalized with a contract, and three operator nodes which represent the operation that we explained before, which is the conjunction, composition, and refinement. Okay, and then the edges connects the goal nodes to the operator nodes and vice versa. And here you can see the example that we show in the paper where we define the vehicle platooning, where basically we express the goal of a following mode of the vehicle. What does it have to do, the car that is following the leader? Well, it has to regulate the speed, has to regulate the steering angle, and has to communicate with the platoon of the leader, and so on. So we use the composition where we talk about the different modules that have to be combined together, and the conjunction when we talk about the same module that have to assume different behavior according to the different assumptions. We'll see some example of that later. Okay, so now how do we translate the conflicts and incompleteness that we see in goal models in terms of contracts? Well, the conflicts, we resolve the conflicts in terms of checking compatibility, consistency, and feasibility, meaning that the assumptions of the contract has to be satisfiable, the guarantees has to be satisfiable, and the conjunction of assumption guarantee also has to be satisfiable, which is not something that is strictly related to the contract, but it just because we want to basically check that exists at least one implementation that does not violate the assumptions. Because obviously every implementation that violates the assumption, it is a valid implementation, but it's not the one that we're looking for. And then regardless completeness, we basically check the refinements of two goals by basically checking if the implication of their assumption is valid and the implication of the guarantees is valid. So checking the size of the sets of the assumption guarantees respectively, but in terms of the actual formula that we're gonna use. Okay, so how do we detect and resolve these conflicts? So first of all, every time the contract is formalized, what we do these three checks. And whenever there is an inconsistency in terms of incompatibility, inconsistency, or feasibility, then we use an SMT solver to capture the unsat core of the formula that we are trying to combine together, where the unsat core is a subset of clauses that are mutually unsatisfiable. So then we connect these clauses to the goals the designer expressed, and we present it to the designer as the conflict resolution strategy. And we see the conflict resolution strategy that Kogomo offers, that approach offers. On the other hand, we have for every time the refinement link is generated, then we check if the refinement is correct, and if it's not correct, as well as before, the SMT solver provides us a counterexample that we also show to the designer. So what are the strategies that Kogomo uses to automatically as well resolve such incompletenesses or inconsistencies? Well, one is the assumption propagation and one is goal priority. Let's see. So let's start from an example to explain this conflict resolution strategy. So this is the goal that we showed that I showed before, right? That formalizes somehow the transmission, the propagation delay, and the steering angle of the following vehicle, assuming the data is correct. So now let's decompose this goal in two sub goals: one that establishes the requirements of the network, and one that actually regulates the speeds. Right, so we can assign these to different components. So if we do that, we can have a goal that assuming a certain range, a transmission range, and we are able to communicate with the leader we are able to compute exactly what is the propagation delay according to the formula, where we take in consideration some size of the meshes that we want to communicate, and the size of the platoon, n, right? Because the propagation increases, obviously, if you are the last in the platoon or the second in the platoon. Okay, so we formulate these requirements in a more refined way. And we also guarantee that if these assumptions are respected, we can guarantee a correct communication with this variable com. Okay, then the other goal assumes the communication. So in this way, we can connect it to the other goal if we compose them, for example. So these guarantees are assumed by this other goal. So and this other goal assuming the communication, then we guarantee that the follower implements the speed and steering angle within the given bounds, which are more refined. So now what we have to do, we have to compose these goals, which again put the goals, combine the goals and simplify, in this case, the assumption of these goals with the guarantees of this other goal. And we would like to refine. So first of all, we connect with composition, and then we would like to refine the resulting goal with the top level goal that we have specified before. Unfortunately, when we do that, Kokomo shows that we have an incomplete refinement, and it shows that why? Because for a vehicle size greater than 10, we have that our propagation delay is not respected. And how do we solve the refinement? Well, that's where assumption propagation comes in play, which basically for every goal that we connect via refinement links, we first of all propagate the assumptions from the lower level goals, the top level goals. In this way, now we are propagating assumption from the first goal, and then we propagate the assumption from the second, from the actually counter example. And we conjoin this assumption to the top level goal. Why? Because as you remember before, we said in the refinement, the assumption of the refinement goal has to be bigger. So by constraining the assumption on the top level goal, we actually respect the refinement, and the top level goal will have a smaller assumption than the bottom level goals. And this now is a complete refinement, and this operation is performed automatically by Kokomo every time a refinement link is created. Okay, now we talk about the conjunction, which instead is used to refine goals in multiple scenarios. So here we're talking about regulating the speed, right? So we're still talking about the speed. We don't want to compose. We want to conjoin, because in this case, the speed of the vehicle should be regulated in some cases by the following leader, in some cases by just the vehicle in front of us, in order for us not to crash. So here we can see an example of conflicts, because since the assumptions are not mutually exclusive, Kokomo detects a potential conflicts that can happen when one goal demands prescribe the vehicle to decrease the speed, and another goal to increase the speed. Since they're not mutually exclusive, this can very well happen. So how do we solve that? And this is where we talk about the mechanism of goal priority, where how am I doing with time? Because I still see 24 minutes here. It doesn't move. Am I good with the time?
Yeah, we have 4 or 5 more minutes.
Okay. Okay, then I should, because I keep seeing 24 minutes this weird. Okay, so the goal priority basically defines a priority among the two goals. We can choose this operation in order for to grant higher priority on one goal, and so that when both assumptions are true, one goal dominates on the other goal. And in the example of before, if we granted priority to, for example, to keep in the platooning distance, so to not crash the vehicle before listening to the leader, then the assumption automatically modified in a consistent way, which is also mutually exclusive. Okay. And finally, one of the contributions of our paper is also the extension, the automatic extension of our goal model via a refinement, via refinement with a library of goals. So formally, what we want to do is that given a goal of our tree that you're building, usually a leaf node, because we want to attach a set of goals which refine this goal, so it has to go below. And given this goal and the library of goals, what you want to do is you want to search in this library a set of goals that once you compose them together, refine the goals that you have specified. Specifically, we don't even have to be that strong. We don't want the assumption to be bigger. We just want the assumption to be satisfiable and the guarantees to be valid. Why? Because then we have assumption propagation that takes care of that. For example, you take out some goal, you select some goals from the library, then you compose them, and the resulting goal you connect via refinement. But after you do that, the assumption propagation will make sure that the refinement is actually a good refinement. So all the assumptions that you gather from the library are propagated up to the tree. Okay, here the cost function that we want to maximize, actually we want to minimize this cost function. We want to see maximizing the set of assumptions, so all the allowed behaviors that are allowed by our components. Why? Because we want to favor the selection of goals with weaker assumption, because we can plug in these goals in bigger contexts. So the weaker assumption, the bigger is the environment that you can use. And we use a greedy strategy. It means that we perform a local optimal selection, but possible suboptimal globally. And this is because it's scalable. So what do? We start from the input goal and the library of goals. Then we choose at each iteration a selection of goals that refines the guarantees of the input goals, and then we keep choosing the goals that relaxes the assumption of each goal, so meaning that can discharge, as we have seen before, where the communication assumption was discharged because another component was guaranteeing it. So we're relaxing more and more the assumption. So that's our cost function, until we don't have no more library, no more components to choose from a library. So we're also maximizing the reuse of the components that we already have. And finally, we return all the goals, all the components. The evaluation shows quite good results, because it scales linearly with the number of returning goals and the size of the library, thanks to our greedy approach. And here we perform some evaluation with the randomly generated libraries, measuring how big is the size of the library and the complexity of each goal in the library, where the complexity is the number of clauses in the assumption and guarantees. Okay, then the standard is proved that the SMT solver, and the completeness is proved by the fact that we search all over the entire library that we have at our disposal. In our example, we can see that we want to refine this retrieve distance goal, for example, from a library. So what we have to do is to have a library of goals, and this will search the space of goals and generate a new goal, which is the result of the composition of all these goals. And if you look inside the goals, you can see that this is formalized by the contracts. which each contract define the boundaries of a component, of a system component, which are connected together via composition. So here you can see that the guarantees of this contract, this charge assumption of this other contract, and so on. Okay, so to conclude, Kogomo, we leverage on contract operations and relations to check the goal consistency, completeness, and to support incremental refinement and hierarchical refinement from the library of goals. We incrementally construct these new formal models that we have defined, which is named contract-based goal tree. And we do that in a modular way with formal guarantees of correctness. And finally, we propose this algorithm to search in a library of goals in a greedy way, which proved great scalability and good results in terms of our cost function.